Okay, this is exam 5. Okay, part A. You make a conical pendulum using a string of length of 0.600 meters and a bob mass 0.150 kilograms. When the bob is moving in a circle at a constant speed, the string is at an angle of 30 degrees from the vertical. What is the radius of the circle around which the bob moves? Express your answer with appropriate units. Okay, so we're going to use this formula that is in section 5.3 and is also in the figure of 5.32. And also the way this problem was modeled or was kind of shown example by was in example 5.20. So yeah, let me just get started. So it's R equals L sine theta. Okay, so this is the equation, and we already have our values. So what we're going to do is just plug everything in. So L would be 0.600 times sine 30 degrees. And then we should solve. Let me just put this in my calculator to make sure. 0.600 times sine 30. I think my calculator is in degrees. 0.600 times sine. Okay, yeah. So the right answer would be R equals 0.300 meters. Now for part B. How much time does it take the boat to complete one circle? Okay, so how much time does it take the boat to complete one circle? Okay, so we're going to substitute R equals L sine theta, and we're going to use sine theta divided by tangent theta, and that should give us cosine theta. Okay, and then should get us 2 over theta over g. And also this was shown in example 5.20 also. And so basically what we're going to do is we're basically doing the same thing we did in part A. We're going to plug in our values. So 2 pi 0.600, basically just plugging this stuff in right here, times cosine 30 degrees. This was the value already given to us. And then G will be 9.81, and that should equal out to be, let me just make sure. Okay, the answer would be T equals 1.45 seconds. And that's for B. Now we're on to part C. Part C, what is the tension of the string? Okay, so what we're going to do is use Newton's second law, and that can be found in section 5.1, and it's the equation 5.1. So let me go ahead and write it out for you. And we're going to use the y component, Newton's second law. So Fy equals 0. Then we're going to do Fy equals F cosine theta equals mg. Then we're going to turn this right here into a fraction. So it'll be F equals mg over cosine theta. And then that out. And then we look back at the values that we had. Okay, so 0, so it'll be 0.150. And then that'll be times 9.81, because remember grams is 9.81, and then meters is 0.150. We're basically just plugging it in again, and then cosine 30, and we solve, and we should be able to get, we solve, and we should be able to get T equals 1.70 newtons. And that's the answer for part C. And also this one was modeled by, well, I wouldn't say modeled by, but this was similar to the example in 5.21. I kind of looked at that and kind of realized how they solved it and used that onto here. Now we're on to part D. Okay, part D. A competition cyclist rides at a constant 16.5 milliseconds around a curve that is banked at 34 degrees. The cyclist and her bicycle have combined of 74 kilograms. What must be the radius of her turn if there is to be no friction force pushing her either up or down the bent curve? Okay, so I'm just going to list out our values. So we have V equals 16.5 milliseconds. We got theta equals 34.0 degrees. And then we got meters equals 74.0 kilograms. And okay, so we're going to use, we're going to solve a similar way like they did in example 5.22. That was the example in 5.22. And the equation they used was R equals V squared G tan theta. So basically, as you can see, we pretty much have all our values. So we're just going to go ahead and plug in. So R equals 16.5 squared, and then G would be 9.81, and then tan would be 34 degrees. Tan 34 degrees, and we should be able to solve. Let's make sure to do this in my calculator real quick. 16.5 over 2, 9.81, tangent 34.0, 34.0. Okay, yes. And then we get 41.2. So R equals 41.2 meters. And that is your answer for part D. So A, B, C, D, E. So part E, what we'll do for that, let me scroll down. Okay, so for part E, we're going to find the magnitude of her acceleration. So we're going to use the equation in 5.4 section. And in 5.4, it's the equation 5.13. And here's the equation. Let me write it down for you. Okay, so that's the equation. So basically, what we're going to do is exactly plug in. So we already found our R, which is right here. So that basically tells us 16.5 squared over 41.2. And then we're going to solve this one right here. And that should get our answer. So I'm going to go ahead and put this in my calculator. 16.5 for 2, 41.2. And then that gets us 6.61. So 6.61 milliseconds squared. And that is our answer for part E. So let's go ahead and turn this over. Okay, so part E, so we're on part F. Okay, so for part F, what is the magnitude of the normal force that the surface of the bank curve exerts on the bicycle? Okay, so we're going to again use Newton's second law, and again this can be found in section 5.1, equation 5.1. well, the equation's 5.1. And then, yeah, so let me go ahead and write that out real quick for you. So, what's it? Okay, good. Fy equals 0. And then we're going to do is we're going to do, it's pretty much similar to what we did earlier. And Fy is n0 minus mg equals 0. We're going to turn this into a fraction. So, turning it into a fraction, we should get 74.0 times 9.81 over cosine 34.0. Now we're going to solve for this one right here. So let me get out my calculator. 0.0 times 9.81 cosine 34.0. And we should get 875. So n equals 875 newtons. And that's your answer for part F. Now for part G, okay, so for part G, an aerobatic airplane flying at a constant 80.0 milliseconds makes a horizontal turn of radius 244 meters. The pilot has a mass 80 kilograms. What is the bank angle? What is the bank angle of the airplane? Express your answers in degrees. So basically, we know that the centripetal force acts towards the center of the circle. So we're going to use this equation right here. So we tan theta equals v squared rg. And also this right here, this equation right here, is from example 5.5. And yeah, so basically we're just gonna plug our equation in. Yeah, we're just gonna plug in. So we know v is 80.0 squared, and then we know what's that, r, radius is 245, which was given to us. 245 times g will be 9.8 always, so 9.8, and then we solve for this. So 80.02 over 2, and then 245 times 9.8, and then that should give us 69.4. Don't forget this right here. You have to include that in the problem. Forget to include that. So equals 69.4. Okay. Now we're going to go to part H. Okay, so for part H, what is the pilot's apparent weight during the turn? Express your answers with their appropriate units. Okay, so we know that the apparent weight is equal to the centripetal force. So knowing this, we're going to again use the equation from 5.13 in section 5.4. And the equation was, okay, AC equals V squared over R. So again, we're just going to plug in our numbers right here. So we have 80.0 squared over 245, which should equal 26.12 milliseconds squared. Okay, so we have that. We're not done yet. So now we have to find the apparent weight of it. So what we're going to do is we're going to do 80 times this, what we got right here from plugging this in, 26.12, and then we're going to plus 9.8 squared, basically find the magnitude, and then that should give us n equals 2230 newtons, and that is your answer for part H. Now for part I, for I, how many times greater than his actual weight is this? So basically what we're going to do is we have to divide n, divide n in w. So we know that n is the answer that we got from part H. So we're just going to list that right here. And then we know that w, so to find w, we have to use this equation, which was in figure 5.32 and also in example 5.21. And the equation was w equals mg. So we already have the values for this. So w equals mg, that's 80 times 9.8, which gives us 784. So what we're going to do is we're going to do 220,784. This is the weight, and this is n. So nw equals, make it neater for you, this right here. And then we're going to solve this. Put this in my calculator real quick. 230,784. Okay, and that gives us 2.85. So n/w equals 10.85. And that is your answer for part I. Now for part J. A sports car moves around a bank curve at just the right constant speed so that no friction is needed to make the turn. During the turn, the driver mass feels as though she weighs x times her actual weight. Find the magnitude of the net force on the driver during the turn in terms of m, g, and x. Okay, so, okay. So we're going to do n cosine theta equals mg, right? And then we're going to do n sine theta equals mv squared over r. This equation right here is in this equation 5.16. So 5.16. So basically what we're going to do is we're going to divide equation 2 by equation 1. And by doing this, we're going to get tangent theta equals v squared over rg. This is the same exact one from part G right here. And okay, yeah. So when we do this, we're going to okay. So we're going to use equation 1. So n equals x mg, and then we're going to put the value n into equation 1. So x mg cosine theta equals mg. So sine theta equals x2 minus 1 over x. And then we find the magnitude force of this. So x mg over x2 minus 1 over x equals the answer mg x2 minus 1. And that's your answer. And also, this whole way I solved this problem, there wasn't really any way I could reference this in the book into that section, but a lot of this was shown in example 5.21 in section 5.4. So I basically did my best to kind of model that, and yeah. So for the last part, so we're on part K. So part K, find the radius of the turn. Okay, so basically we know that tan theta equals v squared from our last problem. And so basically, if you evaluate this more, it equals r equals v squared over g tan theta. Bring this down a little bit. Tan theta. So we combine this, and then we will get tan theta equals x squared minus 1. And then when we combine it, we get r equals v squared over g over x squared minus 1. And is your answer for part K. And that is the radius of the turn. So let me just look at, see if I did everything. So basically that's pretty much all it for exam 5. I did my best. I tried the model, or what am I say? Find the similar examples in the textbook. Kind of looked at how they solved it and like what the steps they did, and tried to kind of take that in. And then also I referenced the equations from the textbook in this section. And yeah, I think that's about all it.